I hope everyone can hear me. Okay. Welcome to the session on Let's Talk Astronomy. Before we start, I just wanted to give that this is not a course, and there is no exam here, and no certificate would be provided for the participation here. And this event is organized or not organized under any affiliation. The materials which we present in this session has been compiled from various sources. On behalf of Let's Talk Astronomy team, I extend a very warm welcome to all of you. This is an online interactive session to discuss about astronomy. We know that the entire world is right now trying to adapt and adjust to the new normal way of living, which is staying indoors. So this is due to the pandemic, which all of us are aware. Under these challenging times, this does not deter us to learn something new, to keep our scientific and engineering knowledge, the thrust for knowledge, to be up. So therefore, some of us who are working in different areas of astronomy and astrophysics would like to engage and motivate our Indian student community to discuss about astronomy and share our experiences. So the objective is basically to present a broad overview of astronomy and discuss some of the challenges involved in pursuing astronomy research and astrophysical research. At the end of the session, so we would also discuss different possible career options which are available for students to pursue astronomy with much enthusiasm. So we strongly encourage all of you to make most of your time here and participate actively in the question and answer session. And again, on behalf of Let's Talk Astronomy team, I extend a very warm welcome to all of you. Many of you might have read about us in our webpage. So who are we? So we are Ph.D. research scholars and postdoctoral research scholars. We are Indian citizens working at different institutes and research laboratories across the globe. So before we go, so I just wanted to make sure that some of the points we wanted to remember for the session. So the talk contained some of the basic as well as advanced science and technical information for students covering from 9th standard to 12th standard. So please be aware of that. And also know that depending on your internet connectivity, some of you may experience a delay in audio as well as video. So follow it carefully. And in case if you get logged out of Zoom, so don't get panicked. So open your Zoom link again and follow the login instructions which are provided to your registered email. So also some of the important instructions is keep your audio as well as video down. Type your questions if you have any questions regarding the session or regarding some of the particular slide. So you can type them in the chat window. So in the next slide, I'll show you where the chat window is for new users. And questions for the presentation. So note down the slide number. So if you have a particular question for a particular slide. Also, when you ask question, please do enter which standard you are typing, which standard you are studying. Also, please do not spam or chat among your friends in the chat box, which is not much helpful for the session. So the overall session is like, first we will take 25 minutes for daytime astronomy. We'll discuss about what we study and what are all the challenges we face during daytime pursuing astronomy. And we'll take some couple of questions in the question and answer session for 10 minutes, and then we'll go to the nighttime astronomy session. And then followed by, again, some question and answer session. In the nighttime astronomy, we cover about stars and other stuffs which we study at night. And after completing the question and answer session, this is very important and interesting, where we would give an overview of career options, what people can do with astronomy, interesting things. So, and after we present that, we also would be happy to discuss some of your interesting questions on both the astronomy, day and nighttime, as well as your career options. So this is how your Zoom window would be. So you would see all the participants here. Below that, you would see a chat window. This is the chat box, where if you have any question, any query about the talks, or some of the specific question you have about astronomy or the talks presented, so you can use this. And again, I am requesting so not to spam the chat box or chatting among yourselves. Use this to ask the questions. So with this, I once again welcome you all for this first session. So, and with this, I leave to our colleague to start with the daytime astronomy. So, thank you. Oops. I'm seeing as daytime astronomy. I think we'll start sharing a screen. So in a moment, our daytime astronomy members would start. Would be there with you. 1 second. Please, I hope all of you can hear us. Yeah.
Okay.
Yeah. Welcome, Supriya. So I can start with the daytime astronomy.
Thank you. I hope everybody is able to hear me. Uh, Thank you very much, Atreya, and welcome everyone again. This session is about daytime astronomy, like Atreya mentioned. So, when we asked you to fill up the form and asked you, you can ask us if you have any questions. Then most of you asked us about the galaxies, the black holes, and many other interesting objects in the night sky. But we received very few questions about our own star, the nearest star, the sun. So we thought, okay, let's inform you in one individual session more about what our star is and what do we study about it in general, what do we know about it, and what do we still don't know about it. So this session is all about that, and we are going to talk about the sun. So here at the bottom right corner of the slide, you see the slide number. So please, if you have any question at any point regarding any of the slides, note down the slide number, put the slide number and put your question in the chat box. And at the end of the talk, we will try and answer your questions. Okay, so let's start. So once we think about like once I say let's know about the star, the first thing we would ask is like, okay, why do we have to study about the sun? So, Sajid, can you go to the next slide? Yeah. We need to study about the sun because we all know our life on Earth is sustained because of the light, heat, and energy that we get from the sun. So it has influence on all our lives, starting from the food we eat and the seasons that we experience, and even the sleep patterns. The when we get up, when we sleep, the day and night, everything is because of the sun. So that's a very good reason to know, like, okay, why sun is so important and what's happening on it. So moving on, uh, also, sun is our nearest star. So it's at a distance of around 150 million kilometers from the Earth, and there are billions and billions of stars in our Milky Way galaxy, and sun is one among them. And by studying sun, so we can understand many other stars in our universe, and that's a good opportunity, and we should take advantage of the fact that we have sun so close to us and understand it in a better way. Again, is that all? Also, the I would say one of the important reasons to study the sun is we know it can be dangerous. So how, I will explain it during the talk, and I'll also tell you, like, if we can avoid that danger that we can face from the sun. So in order to do that, let's move on, see what sun is made of. Okay, let's see the structure of the sun. So the sun has multiple layers. Like if you consider an onion, you have, and you start peeling it, you see multiple layers, right? Sun is something similar. And each layer of the sun plays a very, very important role in producing or transferring the energy finally that we finally receive on Earth. So let's start looking at different layers. So the innermost layer, the interior of the sun, is made of three layers: the core, the radiative zone, and the convection zone. So the core is the innermost layer of the sun, which is at a temperature of 15 million Kelvin. So what does, to get an idea of what 15 million Kelvin is, let's say, let's consider the average human body temperature. That is around 310 Kelvin, or you say 37 degrees Celsius. That's the average human body temperature. Okay, let's take what we know, the molten lava during a volcanic eruption that we see. That's around 1000 to 1500 Kelvin. So now imagine what I'm telling you, in the core, the temperature is around 15 million Kelvin. So it's I know it's difficult to imagine, but it's that high. So what happens in this hot temperature and very dense medium of the core is something that we call the fusion reaction. So in this fusion reaction, the four of the hydrogen atoms come together and it is fused to form the helium atom. But the mass of this final helium atom is slightly less than the four of the hydrogen atoms put together. So the rest of the energy comes out in the form of electromagnetic radiation, or here, let's say the gamma ray specifically. So this heat, or the photons or the gamma rays, all of them, when I say the energy, the photons that is coming out from the interior of the sun, it's all the same. And so this energy travels to the next layer, this huge energy that is now emitted. So that is the radiation zone. So in the radiation zone, now the temperature drops from 15 million Kelvin to around 2 million Kelvin. So, and here the name radiation zone merely comes because of the type of energy transport that is through by radiation. So imagine if you are like sitting in front of the fire to warm up your hands. So you are sitting at a distance from the fire and you can still feel the heat, right? From the heat from the fire. That is the heat from the fire is coming through the radiation that is coming to you through radiation, and you can feel the warm and you can warm up your hands. It's the same process that's happening in this particular zone. So after this zone, it is the convection zone. What happens here is uh, the temperature now goes from 2 million Kelvin, that is coming from the radiation zone, to, and because of the convective processes, it reduces up to 5,700 Kelvin. So what is this convection process? It's again very similar when you boil a pot of water. So what happens when you're boiling a pot of water? The hot water at the bottom of the vessel gets heated up and like goes up, and the cool one at the top comes down, and this process repeats till the whole water is heated, right? It's the same process that is happening also in this convection zone of the sun. So what happens next? Okay, we have all these interior layers of the sun. We see, but of course, we do not see any of these layers. All these layers are masked by a layer called photosphere. Photosphere is the visible layer of the sun. So here the temperature is now going is around 5,700 degree Kelvin. And the name photosphere itself comes because photo in ancient Greek word, it means light. So that is the layer that is visible to us. Though it looks like a smooth layer from a distance, you use powerful telescopes and you zoom in, you see that this layer is made of all these grain-like structures. So this is the image from, it's a very recent image from a telescope called DICIST, which stands for Daniel K. Naur Solar Telescope, which is in the United States of America, which is by National Science Foundation. This is the most powerful ground-based telescope that is currently available. And this is the image taken by the telescope of the photosphere. So each cell that you see here is like as big as uh, like you say the whole of South India put together. So you take an example of a cell here. So these cells are as big as the whole of South India put together. So they are that big. So now you can imagine what scales we are talking about. So moving on, uh, apart after photosphere, there are two more layers to the sun, the chromosphere and the corona. But you might be wondering, I just told you that photosphere is the visible layer. Now I'm telling you, after photosphere, there is also chromosphere and corona. Where why don't we see it? I told you the visible layer. That's because like, okay, imagine this. So you have a very bright light bulb and you have a faint candle. So you place the faint candle in front of the light bulb, then do you see the light coming from the candle? No, right? Because the light from the bulb is so bright that it will completely mask the light that is coming from the candle. So it is the same thing that is happening on the sun as well. The photosphere is so bright that it will mask all the light that can come from the further layers of chromosphere and the corona. Then how did people get to know that there are these layers? So how do we see them? That is, we have the beautiful natural phenomena of total solar eclipse. When the moon blocks the disk of the sun, then that is the photosphere, then you see the other layers of the sun, the outer layers, the chromosphere and the corona. So here is how it happens. I am sure you all are familiar with how the what the solar eclipse is and what happens. So here the moon blocks the sun and then you see the next layers. So if we see in the chromosphere, the temperature now rises from 4000 Kelvin to 8000 Kelvin. So, and this layer is comparatively very thin, not as huge as other layers of the sun. And if you go see the corona is now the temperature in corona usually goes from 1 to 20 million Kelvin. And this is the here we have an image of the corona, which is taken in a during a recent solar eclipse that was in 2017. It passed through many parts of United States of America, and here is the image. You see the outer layers of corona, and the corona itself in means in Latin the crown, and hence the name to this region. It looks like a crown to the whole sun, the outermost layer, and hence it's called the corona. So let's move ahead. So did you notice I told you in this particular image that we have, I told you about different layers and what is all there, but I didn't tell you yet about these features that we also see on the sun, like the dark spots here, which are called the sunspots, and also some bright regions here, which are the flares, and something hanging on the left, which are the prominences. So I haven't told you about that. So what are these? They are on different layers of the outermost solar atmosphere that I'm talking about. And also, I told you that from when I started talking to you about different temperatures of different layers of the sun, I told you that temperature is decreasing starting from the core. And if you might have noticed, suddenly when I reached chromosphere and corona, I started telling you that temperature is increasing. So this is something strange, right? Again, let's go back to this example. So imagine like, okay, you move away from the fire from which you want to warm your hands. As you go away and if you move further away and away, do you expect to receive the heat and for it to increase at any point? No, right? You know that like you move away and you don't receive the heat anymore after a point. So, but in sun, we see that the temperature is suddenly increasing. So let's understand why this is happening. So to do that, we need to understand what exactly sun is made of so that we can interpret all these things. So sun is a huge ball of ionized gas. It's made of different electrons and ions, the plasma moving everywhere. So this plasma, when these ions move, the electrons move, they also carry a magnetic field with them. So this process makes the sun a huge magnet. You must all know that Earth also has its own magnetic field because of the molten core that is moving at the center of the Earth. And the value of that magnetic field of the Earth is around 0.5 cos. So now let's take, for example, a bar magnet. So, and the value of that magnet is around 100 cos. A average magnetic field of the sun is like around 1 cos, but there are the sunspots and other features on the sun which can carry magnetic field of 1000 to 4000 cos. And these magnetic fields on the sun are not just sitting there. Like I said, sun is a huge ball of gas. So because of that, what happens is at the equator, all this material moves much faster than at the pole. And when this motion is happening, they also drag the magnetic field along with them. So this is called the differential rotation. And when this kind of motion is happening, then the magnetic field at some point gets twisted, turned, forming loops and blobs like you see here, which results in the formation of what I told you, the sunspots. Sunspots are nothing but a region of strong magnetic fields. They're so strong and so tightly bound that it will not allow the heating that is happening from the lower layers, and it won't allow the heat to come up. So that's why it looks much darker and it's much cooler than the surrounding layers. So this strong magnetic fields um, that are there, or the sunspots are so huge that it can, most of the times they are even bigger than the size of the earth, and sometimes they're as big as the biggest planet that we have in the solar system, that's the Jupiter. So, and these sunspot, they do not just stop there. The magnetic fields do not stop at the sunspot. And the number of sunspots on the photosphere that we see also is not constant. It follows something called a 11-year cycle. So the numbers are more for certain period of time, and they keep changing, and then they decrease, and they again increase, and this follows a 11-year cycle. So the magnetic field on these sunspots are not just restricted to the photosphere where we see the spots. They further evolve, go to the next layer, that's the chromosphere, and in the chromosphere, they appear on the disk like these dark structures called filaments. They are also ionized gas carrying the magnetic field. And when you look at these magnetic fields from a side angle, then they look like these ionized gases hanging around, which are called, these features are called the prominences. And do the magnetic field stop there? No, of course, there is the next layer, that is the corona. So when the magnetic fields are now stretched from layer to layer, fine. Now imagine like, okay, you have a rubber band with you and you're stretching it, stretching it, stretching it. After a certain point, it breaks, right? It breaks, releasing the energy. The same thing, something similar is happening with the magnetic fields here. It's stretched and stretched, and after a point, it breaks and it releases the material that is carrying with it. So these eruptions are called the coronal mass ejections. So here is a movie of how these coronal mass ejections look like. And if we look at the energy that is released from these kind of events, it's as if you are suddenly blasting millions of hydrogen bombs at the same time. It's the energy can be as huge as that. So what happens? I mean, this so much of energy it's released into the interplanetary medium where other planets are, and it's always emitted in all the directions. But we should be concerned, or we should think about it when that whole mass, the which is ejected now, comes in the direction of Earth where we live. So when this happens, now the mass is traveling towards the earth, then like I said, earth has its own magnetic field, and these particles interact with that magnetic field, causing the beautiful images, the events that we call as aurorae. We see that in the north and south polar regions mainly. uh, like you see in this image, this is it's a very nice event to look at. But if this was all, then it would have been very nice, but it won't stop here. Sometimes the coronal mass ejections are so strong that it can cause destructions. How? You know, we have astronauts in space, they can be affected, and we are dependent on satellites for everything these days. We have so many satellites in the space, and we are dependent for our navigation, the television that you watch, everything is dependent on that. And these can be damaged and in turn cause a huge economic loss for us. So this is what I said, that there can be a danger from the sun, and it would be great, right, if we can predict these events when this is going to happen, so that we can somehow protect ourselves or switch off the satellites during that time so that we can avoid the damage. So, but so how do we learn all this? So how do we know more about the sun so that we understand the sun in a better way to predict these events? We do that using something called multi-wavelength observations. A warning that you all and have to take very seriously is never to look at the sun directly. You should always use a filter when you are looking at the sun. Always remember, you should never look at the sun directly with your naked eyes. Okay, so let's move on. So what are these multi-wavelength observations? So like at some point, if you know somebody or you yourself have fractured a bone of yourself, then you go to a doctor will ask you to take x-ray, right? So that's when he cannot see the bones of your body with the naked eyes, but x-rays are that particular wavelength of light which can penetrate and can see what has happened to your bones. So that's one of the wavelengths. Otherwise, you take a picture of yourself using your camera or your mobile phone, then you don't see your bones, but you just see a picture of yourself. That is in the visible light what you see. So that's another wavelength in which you see. And here is an example of an image taken using infrared radiation, which can measure much cooler temperatures. So you see these people are carrying cool bottles of a drink, and you see them as dark bottles. That's because their temperatures are much lower. Basically, you are seeing different parts of human body or different kinds of images when you are looking at different wavelengths. Similarly, we can probe our sun, or we can look at the sun using different wavelengths, which will help us to study different features on the sun. So this whole technique is called spectroscopy. It is something which also happens when you see a rainbow. That is when a light passes through a prism, it splits into different colors and you can see all the colors. So it's the same technique we use to study the sun as well. But now remember, as the sun emits in all radiation from X-rays to radio waves. Some of these ultraviolet rays, X-rays, are blocked from the sun. It cannot penetrate to the atmosphere of the sun. That's why we have telescopes in the space. Otherwise, we have ground-based telescope to study other wavelengths, even in the radio. So this is one of the examples of how sun spectrum looks like. And now, if you see one such image of the sun taken at different wavelengths, here you see an example. This is the same sun. All the images that you see here is the image of one single sun, but now you're looking at from different, using different wavelengths, and you start seeing different features. The first one, you don't see, you just see more of a plain sun with some spots, but then as you start moving, then you start seeing some bright features, the magnetic fields, so many things happening on the sun, and at the same time you are looking at different regions on the sun. So this is the multi-wavelength observation, which will help us to study how different features on the sun and what is happening on it. So let's look at the different telescopes that are launched by different countries to study this. You will learn more about the telescopes and how it functions in the next session. But here I'm just going to mention some of the solar telescopes. So there are many telescopes by NASA. The recent one being the Parker Solar Probe. I think you might have read about it in the news recently. This particular one is going much closer to the sun in order to study more about the outermost layer of the sun, the corona. I already told you about Dickest, and also there is a recent space mission by European Space Agency, the Solar Orbiter. So these are some of the international solar missions. Coming to the observatories in India, so we have a facility in Udaipur called Udaipur Solar Observatory and a physical research laboratory. So we have a telescope in the middle of the lake over there to study again the photosphere and chromosphere in different wavelengths of the sun. And then we have a radio telescope in Gauri Bidnoor, which is a part of Indian Institute of Astrophysics. And we have another telescope in Kodaikanal, which is the Kodaikanal Solar Observatory, again under Indian Institute of Astrophysics. So Kodaikanal is a very old observatory that we have. It has multiple telescopes. It was formed in 1884, and it was then called Madras Solar Observatory, and it has been recording data since 1904. So you can go to the link uh, here in the slide that you see, and you can access all of this data. It's all available digitally, and you can see how the sun has varied from 1904 till now. That's amazing, right? So these are the existing facilities. Apart from this, I would also like to mention about another upcoming facility before I end this session. That is the space mission, the first solar mission, space mission of India, that is called ADITYA L1. So this is scheduled to be launched by the end of 2021. Like I said, it's a space mission. It carries 7 different payloads or instruments to measure different aspects of the sun, again in different wavelengths, to study different regions of the sun. So I hope, for me, this is all very exciting. Of course, I hope it's the same for you guys. Hope you have learned something, and I hope you want to be a part of these facilities and explore more about the sun. Then wait for our session at the end for career guidance. And thank you. And if you have any questions now, you can start typing in the chat window and we will try and answer. Okay.
Okay, thank you, Supriya, for the talk. And I see that we have got many good questions from the students. So I will read out few of the questions, and we have a short 10-minute question and answer session. And after that, we will be moving to the nighttime talks. So I see the first question from Kalp Dantewadia. And the question is, how are we able to measure the temperature of the core of the sun? So it's a very good question, because we cannot go to the sun and measure the temperature. So how do we get an estimate of this? So basically, the sun is a huge ball of plasma, which is contracting under its own gravity. And as it contracts, the plasma heats up until the gas pressure balances the gravity. So basically, we have a balance between two forces: gravity, which is contracting the star, and we have gas pressure, which is opposing. So when we balance these two forces, we get a final estimate that the core of the sun is about 15 million degrees centigrade. So that's how we measure the core temperature. Moving to the next question, we have from Ishita Dhiman. This is for Atre. How is the temperature of different layers measured?
Yeah, it's a very interesting question. As we know that every body which is at a particular temperature gives a black body emission. So for example, our human body temperature, which is at 37 degrees Celsius, so that glows are in infrared. So if you wear an infrared goggles, so you can see human beings moving here and there. So in a similar fashion, so when the object is hot, then you can measure it at higher wavelengths, higher energies, for example, X-rays. In a similar fashion, if you take images of the sun, if you see in the last slide, you can see images of the sun in different colors. Basically, they are measuring different layers in X-rays, ultraviolet, gamma rays, and infrared. So basically, you take images of the sun in multiple wavelengths, and that measures the temperature of different layers of the sun. Thank you.
Thank you, Atre. The next question from Kankana Roy. what are photons and why do we see the sky blue? Is it anyway related to the photons or other subatomic particles? Shubham?
Uh, yeah, hi. It's a very good question. So photons are basically discrete packets of light. So you can think of light. Well, you can think of light as a wave because light has wave behavior. You might have learned about the Young's double slit experiment, and you have other phenomena like diffraction, which demonstrate the wave nature of light. But light can also act as a particle. The photoelectric effect is a good example of that. So the photon is, you can think of it as discrete packets carrying energy. And this energy is always in discrete packets. And so, for example, an optical wavelength photon would carry a certain energy, and an X-ray photon would carry a lot more energy. And a radio wave or an infrared photon would carry a lower energy than an optical photon. So the energy content in the photon would depend on the frequency of the radiation. And as far as the blue sky is concerned, well, the reason for that is something called scattering. So for the Earth's atmosphere, what we have is something called as Rayleigh scattering, which is very sensitive to the wavelength of the light. So the amount of scattering for a given wavelength goes inversely to the fourth power of the wavelength. So what that means essentially is the smaller wavelengths, that is the bluer wavelengths, get scattered a lot more than the redder wavelengths, and so that's the reason why you see the sky is blue. And the last part of the question is, I'm not sure, but I think the question is, where do photons fall? So in the standard model that we have for particle physics, photons are part of the family of bosons.
Okay, thank you, Shubham. Now, moving to the next question from Castro Chandrabose. Does the sun produce sound? So, Soumya?
Yeah, it's a good question, Chandra. So sound is basically anything like a disturbance that is produced in the medium when there is a change in a pressure or change in particle velocities. So you heard in the talk that there is a layer called the convective zone where convective motions are giving rise to disturbances on the surface of the sun. So since the sun is very dynamic, because of these convective motions, we see a lot of disturbances and vibrations being produced, and these are nothing but sound waves generated on the sun. And solar physicists look at these sound waves and they get the information about what the sun interior is made of, and there is a whole branch of solar physics dedicated to this, and it's called helioseismology.
Thank you, Soumya. Moving to the next question from Saptarishi Haldar. Why the radiation from the corona is so irregular in the structure in solar eclipse? For Supriya.
Yeah, that's a very nice observation from the slides. Yes, that's because like I told you, the magnetic fields that are coming from the lower layers are reaching the corona, and they may not be always very huge. They vary. That's one of the reasons. And corona is very it's not at all dense. It has not, as compared to other layers of the sun, and it extends further away from the sun, even going to the interplanetary region. So that's why you see all the structures in different way, and it also depends on the magnetic field and the density and the ejections that is coming out from the lower layers. So that's why you see it kind of ununiformly distributed.
Thank you, Supriya. One final question before we move to the next session from Kastu Chandra Bose for Sajal. What does sunspot do in the sun? Sajal? Okay, until Sajal is answering. So basically, sunspots are region of strong magnetic field on the surface of the sun. And there is another related question, which is how do we measure the magnetic fields in the sun? And the way we do it is that when we look at the light that is coming out from the sunspot and take a spectra by passing it through and dispersing element like a prism, then we see that the spectral lines have split because of Zeeman effect. And by measuring the split of the spectral line, we get an estimate of the field strength. Okay, I think we can now move on to the next section for nighttime astronomy. And there are many more questions, and we will be coming back to that in the last question and answer session. Okay, so now to Preeti for nighttime astronomy.
Hello, everyone. Good morning. I'm sure you had a great session on our nearest star, the sun. So this session will now focus on the part of the sky that is visible to us once the sun sets, the other half of the day, the night. So we have 3 topics planned for you in this session. The first one will be on stars, galaxies, and planets. The second one will be on cosmology. And the third one will be on instrumentation. So let's get started with our first topic, stars, galaxies, and planets. So we are now going to go on a journey from our seats to the edge of the universe as we know it. And we are going to do it in 10 minutes. So hang on to your seats and brace yourself for a journey much faster than the speed of light. Now, before we get started, let's have a quick look at how we are going to cover this distance of 46 billion light years in 10 minutes. A distance that light itself takes 46 billion years to travel through. Now, in our everyday life, we are used to measurements that are linear in nature, like when you're using a ruler or an inch tape, or when you're adding ingredients while you're cooking. In a linear scale, the difference between any 2 consecutive numbers is the same. So if you look at the table over here, 2 minus 1 is same as 3 minus 2 is same as 4 minus 3. So this remains a constant between 2 consecutive rows. Now, while a linear scale is the most basic form of representing data, it becomes very difficult to represent very large numbers on a linear scale, especially like in a subject like astronomy where you deal with huge numbers. So instead of a linear scale, we use what is known as a non-linear scale. So just observe that graph on the right side for now, and we are going to move to the non-linear scale. In this scale, if you look at the difference between 2 consecutive numbers, that is 10 minus 1, 100 minus 10, 1000 minus 100, it's not the same anymore. But if you take the ratio of these 2 numbers, they are constant. So 10 divided by 1 is the same as 100 by 10 is the same as 1000 by 100. So here the ratio between 2 consecutive numbers remains a constant. And in this particular case, this is a logarithmic scale. Now you see the graph on the right side, between the first, second, third, and the fourth values, how quickly the numbers went up. And I couldn't even put Mount Everest on this graph because of how huge it was on this scale. So this is the sort of scale we are talking about now. So one best example of a scale like this is, you all would have seen this scale used a lot in the last few weeks to represent the coronavirus data for different countries, etc. So if you look at the plot, the y-axis over here, it goes 100, 1000, 10,000, it's multiplying in terms of 10. So this is one of those examples where a non-linear, in this particular case, a logarithmic scale is being used. So now, let's go to the edge of the universe using this logarithmic distance scale. We are going to start from our home base, our own planet, our Earth. So the 10 to the power 7 that you see over there, it refers to the diameter of the Earth in meters. 10 to the power 7 just means 10 followed by 7 zeros. It's an easy convention of writing it. Now we are going to take steps on the logarithmic scale in distance and go to the edge of the universe. So our first step on the logarithmic scale brings us to 10 to the power 8. We are just multiplying by 10 at every step. So last step was 10 power 7, multiply by 10, it becomes 10 power 8. That's it. And this is how we are going to proceed. Now at this step, the diameter of that circle is 10 times bigger than the last step. So in the last step, when it was 10 power 7, it had 1 Earth fit in it. Now we have multiplied it by 10 and the diameter of this circle now can fit 10 Earths in it. So when I go to the next circle, the circle will be large enough to fit 100 Earths in it. So we are going to go to that next step and see what's going to happen. So now about 1/3 way in, as we are going to the next circle, we will start to see moon. So this is the farthest distance into the universe that humans have gone so far. Just keep that in mind once we reach the scale of the universe. Now, as we reach 10 power 9, the final, we easily cover Earth, we cover moon and moon's orbit around Earth. Everything has fit well into that little circle. Now let's move on to the next step, 10 to the power 10. A small part of Earth's orbit itself becomes visible now. Next step, 10 to the power 11. At this point, you start to see a little bit of Venus and Mars's orbit as well around the sun. So you see Venus, Earth, and Mars, a little bit of their orbits. Next step. So 10 power 12, we have gone from a little bit of the orbits to covering all the inner rocky planets of our solar system. So that's Mercury, Venus, Earth, Mars, and the asteroid belt. So how far do you think our next step is going to take us? It might take us to Jupiter, maybe to Saturn. They are quite far away and they are big. Yeah, I don't think we'll go farther than that, right? In the next step, we have covered the whole of the solar system. This is the edge of our solar system. So the outer limit of our solar system is defined by what is called a Kuiper belt. It is a comet-rich area of our solar system that lies just outside Neptune's orbit. Remember, Pluto is not defined as a planet anymore. Just a little outside this region is the farthest any man-made spacecraft has ever gone. That is Voyager 1, which was launched in 1977. So this is the farthest any human-made spacecraft has ever gone. And we are going to see how big the universe is compared to this. So let's go to the next step, 10 power 14. We are now leaving the entire solar system behind. 10 power 15. Now do you notice that the entire solar system that you could see has just reduced to a spot in the sky, a little light. Just like the other stars in the background, there's no difference between our sun or the solar system and the rest of the stars in the background. Next step, 10 power 16. We left the solar system at 10 to the power 13. And we are now 3 steps from there, 10 power 16 on the logarithmic scale. And we have reached the nearest star to our solar system, which is Alpha Centauri, which you might have probably heard of. Now the Alpha Centauri itself is actually a star system which consists of 3 stars, Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Now, just as we zoomed out from our sun, from our entire solar system and came out, what do you think will happen if we zoom into one of these stars? Not back into the sun, but we pick one of these stars and zoom into them. You will likely see that they have a solar system of planets around them as well, just like our sun. These are called exoplanets. Exo means outside. So planets outside our solar system are called exoplanets. It is now believed that most stars in our planet, most stars have planets around them. In fact, astronomers have recently calculated that there are at least 8.8 billion stars with Earth-like habitable planets around them in the Milky Way galaxy alone. 8.8 billion stars is more than the population of humans on Earth. Imagine 8.8 Earths out there, 8.8 billion Earths out there. So let's move on to the next step, 10 to the power 17. At this point, we have come so far that the stars in the background are also moving. So far, they just seem like a still image against which we were moving. Now we have come so far that even those stars have started to move. Next step, 10 to the power 18. At this point, we reach what is called a solar neighborhood. It is just a predefined distance from the sun that contains all our neighboring stars. Next step, 10 to the power 19. You now start to see a little bit of haziness in the image. It's not just stars anymore. They seem like clouds. This is the interstellar medium. Now, as the name suggests, interstellar medium, it is a medium that exists between stars. This is outer space, the region that we always refer to as vacuum. It is not a perfect vacuum. It contains gas and dust particles in it. Next step, 10 to the power 20. Now you sort of start to see some sort of a structure develop over there, right? This is an arm of the Milky Way galaxy. You will see what a galaxy arm is in the next step. 10 to the power 21. This is our own Milky Way galaxy. Almost everything you see in the night sky when you look up is inside that 10 to the power 21 meter circle. Except for maybe 2 or 3 nearby galaxies which are visible in the night sky to us, everything that you see in the night sky is all part of our own galaxy. We don't see anything outside of that when you look up. Now the Milky Way galaxy is a spiral shape, like you can see over here. It's a little bit of a spiral shaped galaxy with arms which are made of these clumps of interstellar medium. Our galaxy contains between 100 to 400 billion stars. The sun is located on one of its spiral arms. So you can see in the image over here, the sun is located on this arm over here. Now, what all does our Milky Way galaxy contain? What all do you think is inside that? So to start off with, it has a wide range of stars, of course, everything that you see in the night sky, all those stars. Now, this is just a plot of the brightness of stars as a function of their temperature. The alphabets that you see, O, B, A, F, G, K, M, are all different categories of stars based on their temperature. That little spot which is blinking above G, 5500 Kelvin temperature, that is our sun now. This is how our sun, the green line that you see, that is how our sun moves on this plot from its birth to its death. So right now it is somewhere in the middle of its lifetime, so it's on that blinking spot. And then we of course have the multiple star systems, just like the Alpha Centauri system that you saw, which had 3 star systems in. And then for each of these stars, they very likely have their own planets. And those planets likely have their own moons too. So these would be exoplanets and exomoons. And then we have different types of nebulae, which are just very dense regions of the interstellar medium. Now a nebula can be either a region where new stars are born, or it can be a region where a star has died with an explosion, spreading its matter all around. And then you have globular clusters, which are collections of stars which are very tightly bound by gravity. There are open clusters, which are again a collection of stars, but they're a little more loosely bound by gravity. Several of these clusters you can see with even a basic pair of binocular if you have nice clear skies. And of course, the most famous supermassive black hole at the center of our galaxy. So now that we have looked at Milky Way, let's go back to our journey of going to the edge of the universe. So we left at 10 power 21, we are now going to 10 to the power 22 meters. Now we are leaving our galaxy behind. You see those small 2 fudges which is next to our Milky Way galaxy, a little bit at the bottom left, this part. They are called satellite galaxies. So they are the small Magellanic Cloud and the large Magellanic Cloud. So these are visible to us from the southern hemisphere on Earth. Next step, 10 to the power 23 meters. At this point, every dot that you see on the screen is a galaxy, is an entire galaxy. Now imagine we pick a dot from the screen and we zoom into one of those dots, one of those galaxies, not our own galaxy. We pick another galaxy from this and we zoom into that. What do you think you'll see there? You'll most likely find everything that you find within our Milky Way, the whole stars, the planets, the clusters, nebulae will be there in each one of them. Now the galaxies themselves can be of different types. So this is a morphological classification scheme for galaxies, which was invented by Edwin Hubble. Hubble is probably someone you have heard of a lot. Hubble's telescope, for example, is named after him. So morphological classification just means that it's classified based on its appearance. So Milky Way is one of the spiral galaxies which falls on this arm of the classification. Let's go to the next step, 10 to the power 24. So you don't see much happening here yet. So you just see more and more galaxies are coming into view. Next part, 10 to the power 25. So at this distance, we start to see the galaxies grouping together. They're clumping together. They're forming clusters and superclusters of galaxies whose sizes are huge, in the order of several billion meters. And one more step, 10 to the power 26 meters. At this distance, we have reached the limit of the observable universe. This is the limit up to which we can look into the universe. We do not yet know what is beyond that limit. We have now reached the point in space and time for cosmology to take over. We will be having Arun now presenting for cosmology.
Good morning, guys. I'm Arun, and now that we have come to the edge of the observable universe, right. Now that we have come to the edge of the observable universe, I think it is time to understand the origin and evolution of the universe as a whole. This study is called cosmology. Now, it turns out that the universe is homogeneous and isotropic. That is, it is same everywhere and in all directions. So sorry to burst your ego bubble, but we are nowhere special in the universe. Now, the question as to whether the universe is infinite and whether it has existed forever has plagued ancient philosophers as well as modern astronomers for ages. Now, one popular question in this regard is, why is the night sky dark, or what is commonly known as Olber's paradox? Now, if the universe was in fact infinite, with infinite number of stars, every line of sight in the night sky, you'll be met with a star. So the night sky will be as bright as daytime. Now, this is something similar to when you're at the edge of a forest, which is infinitely large. So every single line of sight, you'll be seeing a tree. You won't see any patches or gaps between trees. So similarly, every line of sight, we can conclude from this observation is the fact that universe is probably finite with finite number of stars. Now, fast forward a few hundreds of years, and one of the Cuties, he used something you guys are probably familiar with, that is Doppler effect. Right. So I was saying, no. So I was saying, Hubble used the well-known idea of Doppler effect, which I'm sure all of you are familiar with, where you have objects moving away from you or towards you, its wavelength is going to change. So when Hubble observed these galaxies, he noticed that pretty much all the galaxies were getting redshifted, implying that they were moving away from us. Now, next slide. Now, we know that the universe is homogeneous and isotropic, but what exactly is it made up of? In the earlier talk, you heard about stars and galaxies and planets. But as it turns out, all those ordinary matter of which all these things are made up of, plus what you and I are made up of, they make up probably less than about 5% of all the energy density of the universe. So it turns out more than 95% of the universe is still a mystery. Now, you guys saw the images of the spiral arms of the galaxies, those stretching out to the center of the galaxies. Now, these stars, when they orbit around the center of the galaxies, are expected to be moving slower than the stars which are closer to the center. Again, this is thanks to something you guys are familiar with, something called Kepler's laws. Now, when it was actually observed, they noticed that not only is the speed of these outer stars not decreasing, they're in fact staying constant. So that means there is some discrepancy between the theory and what is actually observed. So this indicated that there was some mass out there towards the edges of the galaxies, which was holding these stars in place. And obviously we couldn't see this matter. So that is what is called as dark matter. Now, thanks to Hubble, we have established the fact that the universe is in fact expanding. Now, when this rate of expansion was measured, it turns out that the expansion rate is in fact speeding up instead of slowing down like what is expected. It's sort of like if you throw a stone up, you expect its speed to reduce because it's being pulled back by Earth's gravity. Similarly, we expected the galaxy's expansion to slow down because of collective gravity. But it turns out the expansion is in fact accelerating. This is something like somebody has attached a rocket to the stone as it is being thrown up. So there is something which is pushing the universe farther apart faster. And this something is what is referred to as dark energy. So the mysterious 95% of this energy density of the universe is your dark matter and dark energy. Now, yeah. Now, just like humans are born and go through different stages of life, your stars are born and it goes through different stages of life. Similarly, the universe also evolves in different stages. But what exactly causes these different stages to occur? With expanding universe, something from the laws of physics that you're familiar with, the densities decreases, the temperature and the corresponding energies decreases. And since different physical processes require different energies, the universe shows different stages or different epochs in its evolution. So in effect, it's the expansion of the universe and the corresponding energies associated with that particular epoch that is responsible for showing these different stages. So if we rewind a video of the expanding universe, you will see that all the galaxies eventually come back to a single starting point. And that is where we have the beginning or the birth of the universe, the Big Bang. So at this point of space and time, all known laws of physics break down. Now, the next important stage is dubbed as the inflation era. And this happened when the universe is about 10 power minus 36 seconds old. That is, the universe expanded so rapidly. In fact, it expanded 10 to the power of 26 times within a time of over 10 power minus 32 seconds. The number might not register all that well. So think of it this way. It's like a strand of hair growing to the size of the Milky Way in that small fraction of a second. And what this inflation did was it introduced tiny wiggles on the smooth universe, which was important at later stages for formation of structures. Now, as the universe expanded, again, it cooled further. When the universe was about 1 second old, protons and neutrons and electrons started forming. They were still interacting with light. Fast forward a little more, as the universe was about few seconds to few minutes old, the nucleus of first atom started forming. That is, the protons and the neutrons combine to give you the nucleus of lighter elements like hydrogen and helium. Then, when the universe about 380,000 years old, the first neutral hydrogen atoms formed. Light and matter were no longer interacting and they evolved separately. Now, the data from this era comes to us from a very important source that is called the cosmic microwave background radiation. Then the universe went through a stage of darkness, something called as cosmic dark ages. And then when the universe is about 1 billion years old, that's when the first stars and galaxies started forming. Remember the ripples that were formed initially. So from there, the seeds were provided for the first stars and galaxies to form. Then again, move forward to about 13.7, 13.8 billion years from the Big Bang. We are at the present, where we see the observable universe that you saw in the previous session. So all atoms, except hydrogen and helium and very trace amounts of lithium, were created in the stars, and went all the way till iron, I should specify. And heavier elements, heavier than iron, were created by the eventual depth of these stars in the supernova explosions, right? So from the initial light or radiation from cosmic microwave background radiation, we can probably pretty much figure out where the stars and galaxies and eventually where you and I came to be. Next slide. So here is a short video which will run you through the sequence of events that we saw in the previous slide, starting with the first light that we can receive, that is a cosmic microwave background radiation, to the cosmic dark ages, then the ripples in space and time giving you the first structures, stars eventually clustering up, giving you certain larger structures, the galaxies being formed, and that's the visible universe that we see today. Next slide. Right, so the question is, how do we know all this? This is where observations play a very vital role. The farther away, farther we see, older the light is. So I'm sure you'll be familiar with the fact that you're looking at the sun as if it was 8 minutes ago. So if you're looking at light coming from 1 billion light years away, it's a light 1 billion years old. So farther away you can see, the older the light that is coming to you. So one significant observation is that of the cosmic microwave background radiation. And the latest probe to study this in detail was a Planck satellite. Now, remember this CMB is the oldest light in the universe that we can detect. This light was emitted when the universe was very young and when the first hydrogen atoms were formed. So there's a light that is coming to you even before the stars and galaxies formed. Now, the galaxy surveys like Euclid probes, it probes the evolution of dark matter and structure formation. So you have telescopes in space that will map thousands of galaxies across the sky and study how they are distributed. Now, as the universe evolves and expands, this distribution changes. And this can give us a clue about the nature of dark matter and probably dark energy. The square kilometer array, it's an array of radio telescopes which will be used to detect the energies emitted from hydrogen atom. Now remember, hydrogen is the most abundant element in the universe. And using the energy that it emits, we can look back to the time when the first stars and galaxies were born. Next slide. So now, how do we go about setting up these precise instruments? For that, we will head out to the engineering and tech guys, and they will tell you more about their toys. Thank you.
So, hello everyone. So my name is Avinash, and I'll be heading the technology and engineering part in astronomy. So I work as a postdoctoral fellow in engineering at one of the largest observatories in the world in the island of Hawaii. To all the aspiring engineers out there, you have a huge role to play in the field of astronomy. Just because you're in engineering, just don't think that there is no role for you in astronomy. There are ways to get into astronomy, and there are huge amounts of efforts in engineering, cutting edge precision engineering and technology happening in the field of astronomy. So most of the discoveries which have been mentioned so far, even in daytime and nighttime astronomy, have been made possible or validated with the help of cutting edge engineering in the field of astronomy. So you can see in the background one of the largest set of observatories around the world. And maybe you can ask a few questions about why there is a laser pointing at the sky and shooting lasers everywhere. So going on. So what is engineering mostly about in astronomy? So most of instrumentation and engineering in astronomy is about building a great lens. You all have seen lenses in schools, in labs. So it's all about building a great lens to collect the faintest of light coming from millions of light years away. Combine that with a super sensitive camera to convert that light into pictures and other forms of data which we can analyze to understand the observable universe. So this is the kind of lenses that you might have seen in labs, in your school labs, which focus the light at a central location. Mirrors also do the same thing, as you would have noticed, especially the concave mirrors. And most of the telescopes around the world use some form or the other of concave mirrors. So how has astronomy progressed over the last 400 years? How far have we come in making cutting edge engineering to observe the universe? It all started with a very familiar name, Galileo, who you would have heard of in your textbooks a lot. On the left side is the telescope that he built, and he used his eyes as the sensors to copy what he saw and draw the craters of the moon. So this was probably the first proper scientific astronomical observation that anyone has ever conducted. And after that, people started building bigger telescopes with bigger mirrors and lenses to collect more light, and they use that for focusing it into photographic plates. What you see here is a photographic plate which a person is analyzing with a magnifying glass. So this was in the late 1800s and the early 1900s. So this was how astronomy was done. And what you see here is a negative of the photographic plate. And these plates were very similar to the film cameras that your parents might have used in their childhood. So what you get, the image quality that you get with a telescope on a photographic plate would be something like this. This is the M31 galaxy, which you see in good detail on a photographic plate. And now we come to the cutting edge of engineering and astronomy today. Yeah, this would be a household name by now. About 30 years back, we humans sent a telescope to space so that we could see the stars without the degradation of light by the Earth's atmosphere. So you can see the camera, the digital camera that is in Hubble. And you can see the kind of pictures that have been taken by Hubble. But one question, you have seen pretty pictures of galaxies, stars, etc. all over the internet. But is astronomy all about pretty pictures? Is that all there is? Of course not. So it's about how we use these images and this data to discover new things about the universe. In this example, let's assume that there is a planet orbiting a star several light years away from the Earth. So even using the best telescopes on Earth today, we cannot directly see if there is a planet orbiting that star, especially if it is an Earth-sized planet. Our telescopes are not powerful enough to see that planet because the star's brightness is so high that the we will not be able to see the planet beside the star. So how do we understand that there is a planet rotating around the star? So you can see here, this is the amount of light that the telescope is recording over a period of time. So especially when the planet comes around and passes in front of the star, you can see a dip in the starlight because the planet is blocking the starlight a little bit. And we observe the star for a continuous amount of time, and we see that this dip is happening again and again and again, and we think, oh, there should be a planet rotating around the star. And depending on how periodic this dip is, we can easily understand how far the planet is from the star. So this is important in understanding whether it is in an area where it can have water, or whether it is like Jupiter, or whether it is an ice giant like Neptune or Uranus. So that is one way of understanding how using the light to understand what is happening in the universe. In the same way, for example, instead of understanding the light by itself, we can use a prism in front of the starlight which is coming in, and you get a slew of colors coming out of that prism. But you see in between, as Supriya had said, when you analyze the electromagnetic spectrum, and you see the color spectrum coming in, you see a lot of colors which are missing from the spectrum. So these will be the colors which would be absorbed by the planet's atmosphere. So these are examples of, for example, if you look at Venus, and you see because of the high amount of carbon dioxide in the Venusian atmosphere, you can see that there is a big dip in where the carbon dioxide color should be. Carbon dioxide is absorbing a lot of color in this wavelength. So for example, if you look at Earth from a long distance away, you can see that the water vapor in the Earth's atmosphere is absorbing a lot of light. So this is how we understand whether there is a possibility of life on planets outside of our own solar system without actually seeing them directly. So where do you want to be when you grow up? So you can build an array of instruments, whatever you want to be. But if you have to choose, would you be in radio astronomy, where you will be building huge radio antennas? In this case, this is one in China, which spans for almost half a kilometer. And it is built for looking at black holes, active galactic nuclei, and various other celestial phenomena. Or would you be working on large array of supercomputers to combine the data from various telescopes around the planet? So you must have seen the image of this black hole, which has been quite popular over the last 1 year. The image of this black hole has been synthesized with the help of so many radio telescopes around the Earth, working together synchronously and combined with supercomputers to analyze the data and synthesize this image. This did not come from just one telescope. So, or do you want to do you want to build huge mirrors on mountaintop telescopes which can see back in time to the first galaxies ever formed in the universe? Also, you get to play with a lot of liquid nitrogen, since the cameras need to be cooled to almost minus 200 degrees Celsius. And this is the final frontier. As for ultraviolet and X-rays, there is no choice but to go to space, because the ultraviolet and X-rays don't reach the surface of the Earth because of the ozone layer and the water vapor which absorbs these wavelengths. So the only way to do it is to send balloons or satellites to space or near space to observe the UV and X-rays which are coming from celestial bodies. As you can see, both of these images are taken from 30 kilometers outside of Bangalore. This is at the MGK Menon lab in Bangalore, where they're working on one of the UV instruments. And this is a balloon experiment which is conducted by the Indian Institute of Astrophysics. A balloon which is sent with a lot of sensors to the edge of space to detect the UV rays coming from celestial bodies. So in India itself, there is a lot of scope for UV X-ray instrumentation, even visible, the infrared and radio astronomy. So what all do we do? So you can, one of us, for example, works on the concept of how we combine the data coming from the radio telescope in space with the data from Earth. And we have people who use lasers on telescopes to reduce the effect of the Earth's atmosphere on starlight. And we have one among us who does precise control of mirror shape for huge telescopes. And then there is someone else who is building CubeSats for creating for ultraviolet missions. And finally, there is someone also who are building instruments to creating 3D maps of the night sky. These 5 people are among the 5 of us. So if you have any questions regarding this, shoot away. So this is time for the 10-minute question and answer session. And I will transfer the mic to Prasanna.
Thanks, Avinash, for a wonderful talk and previous speakers. So we'll go to the Q&A sessions. We have got very nice questions in the Q&A session chat box. Okay. So the first question is from Diksha. On what basis are the boundaries of galaxy defined? And Preeti will take this question.
Hi, that's a wonderful question. So what happens with the galaxy is you define a galaxy depending on its main constituents would be the stars, and you have the interstellar medium. Now, just like you have the solar system where all the planets are bound by gravity to the sun and they're going around the sun, you have the stars in the interstellar medium. In our galaxy, for example, gravitationally bound to each other and bound to the black hole at the center of our galaxy. So the whole galaxy is rotating around this central black hole, just like the planets are going around the sun. So we can find out which are these objects which are gravitationally bound together and form one unit. So we know that, okay, these are the stars which are going around our black hole. So these all stars belong to our galaxy. So that's a way to define the edge of the galaxy. And though galaxies are huge, the distances between the galaxies are much bigger. So there is not a lot of confusion in that regard. So you define it by, so this is a limit up to which the stars and the intergalactic medium is bound to the central black hole in our case.
Thanks, Preeti, for the answer. So the next question is from Dhanush, and his question is, how big is our universe in kilometers? He's a 9th standard student, and Sandeep will answer this question.
Yeah, Dhanush, it's a very interesting question because we are trained to measure distance in kilometer as we are staying on Earth. But in universe, if you do, it will be disastrous, as already told by Preeti in her talk. So she started with the center of universe, or what you say, we are living in the place she chose to be center. And we are living on Earth, and the edge of the universe is around 46 billion light year. So the term she chose was light year. So the 1 light year you can convert into kilometer, and you can get the desired unit you want in kilometer. So 1 light year is the time the light travels a distance in one year. So the speed of light is 300 kilometers per second. Then you can convert into kilometers. But it's very disastrous, because if you put that number, there will be many zeros, 20, 30 zeros. So you cannot pronounce it very well. So it's better to use light year. So, but anyway, you can do your experiment with kilometer. Okay.
Thanks, Sandeep. So next question is from Adi Kumar. Question is there any way to tell the number of galaxies in the observable universe? Shubham will answer this question.
Yeah, hi. That's a very interesting question, and it's still an active area of research. So yeah, it's a difficult question to answer. Well, because the universe is so big, and because the distant galaxies are very hard to observe, because as we know, the radiation or the intensity of the radiation falls off as the inverse square of distance. So it gets harder and harder technology-wise to detect distant galaxies. So one of the groundbreaking surveys that was done by Hubble is called the Hubble Deep Field study, which was conducted precisely to answer this question. And what was done is Hubble spent many hours and multiple orbits staring at a region of the sky which was previously thought to be blank. There were no stars and no known galaxies in that region, and we just thought that it's a blank region of space for a long time. And so Hubble just stared at the region for many hours and just collected all the light from the region and just stacked all those images and just added all the signal for many hours. And eventually the image that they got is an iconic image called the Hubble Deep Field image, which revealed thousands upon thousands of galaxies in that small region of space. So now what you can do, a simple calculation to calculate the total number of galaxies would be to take the number of galaxies you saw in that deep field image and to multiply that with a factor that corrects for the total area of the sky. So let's say you observed only 1 degree, and because it's a 360 degree, assuming that there's a uniform distribution, you just multiply that and correct for that factor. And it turns out that if you do that, the amount of the amount of galaxies in the observable universe turns out to be around 200 billion, which is 2 to the 10 raised to the 11. But simulations have shown that the actual number is actually higher than 1 trillion. So I hope I've answered that question.
Thanks, Shubham, for the answer. So next question is a dynamic question, and it is from Anaga. So the question is, do the galaxies expand? And if so, what makes it to expand? And what happens if two galaxies interact? This question will be answered by Akanksha.
Hi, that's a good question, because the first thought that comes to our mind when we see an expanding universe is that maybe even the galaxies and stars are expanding with it. But we have to keep in mind that the rate at the force with which the universe is expanding and the force with which the particles in a galaxy are coming together, we have to compare these two. It's like a push and pull problem, you know. So the gravitational force in galaxies is much more stronger than the force which is pulling the universe apart. So that's why while the galaxies themselves are collapsing, but the universe as a whole is expanding. So no, the galaxies are not expanding, but they may be interacting. And if they are interacting, for example, the Andromeda and the Milky Way, they would eventually come closer. So the reason they are coming closer is due to each other's gravitational pull. So usually galaxies are like a collision-less system. What we mean by that is that even though there are so many stars, they are so wide apart that they won't really be colliding with each other. So even when galaxies will interact with each other, they would not be much effect on the other stars within the galaxy. So so I hope this answers the question. Thanks.
Thanks, Akanksha. So here's the final question. So this is from Shubhiksha. The question is, I see a varied number of colors in our galaxies. How are the colors formed? Does it indulge any type of process to produce such colors? And this will be answered by Avinash.
That's a great question, Subhiksha. So as Preeti already explained in her first question, the galaxies are primarily composed of billions of stars, and then there is nebulae, which are composed further of dust and gas. So color of galaxy is primarily determined by the composition of the number of stars, the gaseous nebulae, and the dust. Okay, so stars, there are varied masses. Some of them, like a sun, are like they're labeled in units of solar masses. So we call our sun as 1 solar mass, and then there are stars which are 100 times the mass of the sun. And as you can see, and as you would have already seen in the first talk, the daytime talk, sun is primarily looks yellow in color, right? And if you go higher and higher in mass of the sun, the color changes to green, and the most massive stars look blue in color, the supergiants, which are almost 100 times. It's because their surface temperatures are very high. Sun has a surface temperature of around 6,000 Kelvin, whereas the supergiant has a temperature somewhere in the range of 30 to 50,000 Kelvin. Okay, and they primarily behave as a black body, and using that, if you can determine where the peak emission is. So as you can see, the cooler stars emit in red, and the most massive stars emit in blue. Now coming to the nebula, they're primarily composed of the most common element found in the universe, which is the hydrogen, right? And then there is helium, then there is oxygen, which is produced in the stars, and there are trace elements, trace amounts of higher atomic mass elements. So the emission from these nebulae is primarily dominated by emission from these lines. Hydrogen actually emits in the whole spectrum. It has lines in the blue and it has lines in the red, whereas oxygen primarily emits in the green. So what you see in a galaxy is a summation of all these light from all these sources. So when you combine, and depending on the composition of each of these galaxies, you will get different colors. So spiral galaxies will show you more blue emission because they have more massive stars, whereas the ellipticals, which have more evolved stars, which have cooled down, they will show more yellow emission because of the same fact. I hope that answers your question.
Thank you, Avinash, for the answer. So there are many questions which are asked by different people. So we are keeping track of them, and towards the end of the session, we will answer some of them. Also, if you have any other questions, keep typing them in the chat box, and over to the next session.
Hi, everyone. The last two sessions, you saw exciting things about day-night and nighttime astronomy. So right now, some of you have started asking the question that how do you want to, if you want to have a career in astronomy, what is the way to go about it? So in this session, I'm going to explain to you just after your 10th or 12th standard, what path you can take so that you can pursue astronomy as your career. So what all we looked at till now can be broadly classified. Mainly the research area in astronomy can be broadly classified into 3 different groups. One is theory, simulation, modeling, and the other one is observation and data analysis, and the third one is instrumentation. So what exactly is theory, simulation, modeling is? You develop your models based on your mathematics and your physical processes, what you understand. You develop a set of equations and you develop a model. For example, you can develop a model saying this particular star is supposed to behave in this way according to my model. But you cannot verify it because you have just developed the model. You don't know whether it is correct or wrong. So what you can do is you can go work in observation and data analysis. What you do there is you take the data, that means you observe this particular star for which you have developed the model, and you take the data and analyze the data in order to see whether your model is matching with what you're observing. So in order to take the data from the star or to collect the light from the star, you need a telescope. So that telescope is developed from an instrumentation team. So basically these 3 fields are interconnected. So if you have to do theory and theory, simulation, modeling, you should also have a little knowledge of observation and data analysis, and people who work in observation and data analysis also know about instruments. So in order to have a career in this field, if you want to work in the first 2 things, that is related to theory, observations, you should have very good physics and maths background. And if you want to work in instrumentation, you have to have a very good engineering background. So both from the physics background and engineering background, both can have a career in the astronomy. So this is a roadmap to pursue research in astronomy. Research in the sense, in order to pursue research, that means to become a scientist or to become a professor, the path is you have to do a Ph.D, that is Doctor of Philosophy. So you all know right now, if you are in 12th standard or 10th standard, the next phase for you to decide what you're going to do for your bachelor's. That means either you're going to do bachelor's in science or bachelor's in engineering. So if you do bachelor's in science with major in physics, then you can go ahead and do master's in science with also majors in physics. Then you can get into one of the institutes in India to pursue PhD in astronomy. For that, in order to go there, you have to clarify an entrance exam. Like you have entrance exam after your 12th standard, right? You give NEET in order to join engineering or medical. In the same way, you have to give an exam that is a nationalized test called JEST, GATE or NET. Similarly, in the case of engineering, after you finish bachelor's in engineering, you can give GATE and then pursue your research in astronomy. So you can get into doing PhD in astronomy or astronomical instrumentation. In some of the institutes, there are also options where you can just do engineering, that is bachelor's in engineering, and directly go on to pursue PhD in astronomy. So this is a whole picture of how you can pursue research career in astronomy in India. So along with these nationalized tests, you also can attend some of the individual tests from the institutes. Like if you remember a few years back, you had different tests for after the 12th standard, like you used to write IIT, JEE, IEEE, and etc. So in the same way, at this stage, you have different tests which you can give to the which is specific to the institute and join the institute. So what are the institutes which offer these courses? For the first case, that is in your bachelor's level, you can do bachelor's of science or engineering in any of the institute you prefer, because you just have to choose your major, that is your physics, or in engineering, one of the branch of engineering. Later, if you want to do a master's program in astronomy, there are few universities across India which offer astronomy at the master's level. So you can check in the eligibility in these institutes and get into one of these institutes and do your master's. After this, when you have to go for the PhD program, there are these 8 institutes which are the premier institutes in astronomy and astrophysics, which have a dedicated program for PhD in astronomy. So you have 3 institutes in Bangalore, that is IAC, IA and Aurorae, and there is ADITYA in Nainital, and 2 institutes in Pune, IUCAA and NCRA, EIFR in Mumbai, and PRL in Ahmedabad. So these, when I say these are the premier institutes, that means they have a dedicated program for research in PhD in astronomy and astrophysics, and their intake can vary about 10 to 15 students per year. So if you did not get into one of these institutes, or if you want to pursue in any other university or ISARs, there are also options that there are many ISARs and universities which also offer the PhD program. So either you can get into one of those institutes for PhD, or you can do in any of these universities. So after this, the next thing is, what if you don't want to do PhD in India and you want to go abroad? That means after your bachelor's, you decide to go abroad, then you can go to 2 different continents. That is, you can go up to USA or Europe. So in both the case, for both the places, when you have to go, you have to qualify an English proficiency test, GRE and TOEFL for US and IELTS for Europe. So after your bachelor's, you can clear the test and apply in the universities, do the master's and then PhD. And one important thing to note is, when you are doing the PhD in any of these institutions, you don't have to pay any amount. Like you pay for your admission fees, you don't have to pay anything. The government will offer you a fellowship or a stipend of about 32 to 35,000 per month if you are doing PhD in India. And if you're doing abroad, you get to about 1,000 to 2,000 US dollars, depending upon which institute or which country you are working in. So this is one of the important things you can note down. Along with that, if you want to avail for some fellowships at this stage, like when you are in your 12th standard or when you go to your bachelor's, there are 2 options which you can check out. One is KVPY, which is an exam which you qualify and you get the fellowship. Other one is the Inspire Fellowship from Department of Science and Technology. So you check out these 2 things, which we will also put it on our website. So if you want to avail for any fellowships and apply for this at this stage, you can also do that. So before you actually decide to take up a research career in astronomy, like you're not sure, you don't know whether you want to do PhD, but you want to explore it, what you can do? You can have these premier astronomy institutes I mentioned to you. They offer summer and winter schools and during the in the year. So you can go for about a month or 15 days in one of these institutes like IIA, IUCA, etc. and see whether you like it. And also you can apply for an internship during your bachelor's and master's and in one of these institutes. And you can also do your bachelor's and master's project, the 6-month project which you have to do in these institutes. During this time, you can interact with the people there and you can take part in the events and decide whether you like astronomy as a career, whether you want to pursue it. So what can be the job prospects? Like, you know, if you don't want to do PhD and you want to finish your bachelor's or master's and still want to be a part in astronomy, like you want to contribute to the field of astronomy, what you can do is you can take up technical jobs in after your bachelor's or master's in technical fields in ISRO, IAA, IUCA. So these institutes recruit people from different engineering backgrounds, for their different projects to contribute in the specific part of the project. So if you are from an electrical engineer, you will contribute to related to electrical and electronics. If you are an optical engineer, you will design a telescope. So you can contribute in the project. You don't have to pursue your PhD to be a part in astronomy. Other thing is, even after PhD, if you don't want to do if you don't want to work as a professor or a scientist in an institute, you can also take up a research job in an industry. So there are many industries which work in telescope manufacturing, so you can apply for a job there and work there. So after all this, if you are not sure about a career in astronomy at all, I don't want to have a career in astronomy, but for me it is a hobby. So what can I do? So you can visit local planetariums and attend their skywatch sessions. So there are 47 planetariums across India. We will put up our details on the website. So you can go visit their skywatch sessions and attend their public talks and be interested in astronomy. Or you can join one of the astronomy clubs which are there, the local clubs in your city, and they host a lot of programs and they invite astronomers from different institutes, so you can be part of it too. Or you can also take part in national and international astronomy Olympiads. And there is a website called zooniverse.org where there are some cool astronomy projects, which is in a very basic level, which you can do and understand, okay, whether it is interesting. And along with that, there are some institutes which conduct small courses like 100-hour certificate course and some REAP course in planetarium, which you can attend as a fun and you can learn astronomy. If you have any questions, please type it in the chat and we'll be happy to answer. Thank you.
That was very interesting, Ramya, to cover up all the path which students can take as a part of their career to take astronomy. So now it would be a good time for us to take some questions. We have a lot of questions asked by students. Okay. Okay, I see a question. Okay, I'll start with this before people start putting their names for the questions. Kushi Gupta asked, does ISRO or NASA employ PhD astrophysicists? Yes, ISRO and NASA do have astrophysicists. Of course, ISRO and NASA also have, it's a big organization, so that has a lot of instrumentation people, scientists who deal with astrophysics. Not only that, it has rocket engineers, it has electrical engineers, mechanical and computer engineers, because as you might have seen that astrophysics has involves so many science branches. So so if you want to make an instrument, then you need to be good in engineering. So the straightaway answer is yes. ISRO and or NASA, they do employ people with PhD in astrophysics. Yes. And any other question? Okay. And there is a question from Kankana Roy. I want to be an astrophysicist of NASA. It's my dream. How can I get there? So, okay. This would be interesting question. So, yeah, I know working for any space organization, no matter whether it is with the United States or with India or European Space Organization or Japanese Space Organization, all of them are doing an exceptional job in understanding the mysteries of the universe, and then also to improve our technology. So so basically the issue is like to become an astrophysicist of NASA. So what you have to do is, from my understanding is, so you have to first complete your degree, whichever it is. So if you want to be an astrophysicist, then you have to have a PhD, and then you have to do some postdoctoral fellowships where you learn some of the interesting stuff to steer your research and then lead some of the interesting science programs. Not only that, also if you have good instrumentation, then that also adds a value. And keep applying for fellowships, and NASA do offer a lot of fellowships, so keep looking for that. And yeah, that's about it. And okay, there is a question from Kirti Sri Supala. What to take after class 12th to become an astronomer? Prasanna would be answering this question.
Thanks, Athray. So this is a very interesting question, and many of the college students get this kind of question. They're interested in astronomy, and fortunately, there are different paths. If you are having keen interest in engineering side of astronomy, you can choose to go in BE, BTech, followed by masters, and then do a PhD in technology. That's what we like. I am personally have done this particular part. Whereas if you are interested in science aspect of it, you can choose to go in BSc, MSc stream, as well as there are a lot of integrated BSc, MSc programs which also lead towards PhD. So all the options are available as at this point of time. There are many institutes in India as well as abroad who offer such courses. So it's all depends on your interest, and if you're engineering interested in engineering, go for the engineering side and come back to astronomy. Whereas if you're interested in science, go for the BSc, MSc, physics or mathematics. But of course, there are other branches of astronomy these days, so you can have a look at that as well. Thank you.
I didn't unmute. I'm sorry. So thanks, Prasanna, for the answer. The next question we have from Kushi Gupta. What entrance exams after 12th other than KVPY or JEE mains are available in India to get into research, which would be answered by Varun?
Yeah, so basically, apart from these two exams, you can have your basic university exams in which you can have your regular BSc, MScs, and after that you can write those entrance exams for the JEST or NET, whatever those exams are there. And with that you can join into the astronomy actually. I hope I have answered your question.
Okay, that's great. So Thanks, Varun, for answering that question. I have been looking for the questions. Okay, there is a question from Subiksha. Choosing engineering helps, then what field should we take? Okay. Mechanical.
Maybe I'll answer that part. So,
or mechatronics.
Yeah, so if you're choosing engineering stream, typically if you see doing PhD, MTech PhD in astronomical instrumentation in India, there is an institute called Indian Institute of Astrophysics, which offers such course. So wherein the eligibility criteria is BE electronics, electronics communication, instrumentation, mechanical engineering, and similar branches. So when I say similar, you have to check the eligibility criteria. It's clearly given in their website. So we are also going to put some Q&A FAQs rather on our website. So for which you will get an email. So on that website, there are a lot of resources compiled. So maybe you will go through that as well. But yeah, if you're going towards engineering, there are a couple of branches which are eligible for doing astronomical instrumentation in that time. Yeah.
Okay, thanks, Prasanna, for taking up that question. So yeah, there is another interesting question from Anaga. My interest is more towards practical applications rather than research. What could be the possible options? Which would be answered by Sandeep.
Yeah, it's very interesting question in a sense, like astronomy, which is driven by the questions. So it's mainly research-oriented branch. So it's very hard to find a job where you have to do which is application-oriented. So maybe I think that if you are in the instrumentation side, then you have skills that can be used in generating some applications. Like suppose if you are in a team which deals with the aeronautics of rockets, that can be used in aeroplane dynamics, which is quite applicable in our daily routine. So these are the few possibilities I can think of. I think my other friends will answer other possibilities. I hope this answers your question.
Yeah, thanks, Sandeep, for that, for taking that question. So I may just want to add one more thing to what Sandeep has said. So practical applications in the sense that if you take an engineering side, as Sandeep mentioned, that instrumentation is one of the place where one can contribute to that. And also when you look at astronomy, so it's not only that, so any observations for any space missions. So like a practical application, for example, if you want to work on a GPS satellite, and that's a practical application. So those kind of things for any space mission or any ground-based systems. So those things, instrumentation related and software related things are very useful. For example, image reconstruction. So if you look at any artificial intelligence system these days, so that comes with various aspects. So one of the things is like image imaging, and how do you want to make, if you want to look at some pattern from a set of data which people are doing, so how do you want to get that? So how do you train your computer to look for features? So all these mobile phones, if you look at it, when you move towards different directions, it captures your face, it recognizes your face in Facebook and other applications. So those ideas and technologies are also useful for astrophysics and various researchers. So you can work on those algorithms, and you need not have to worry about research, but you can work on those algorithms which are useful for other day-to-day activities, or the as you just wanted to bring the same word which you said, the practical applications. Yeah, I hope that answers your question. And then I'm looking for some other question. There is another interesting question from Adi Kumar. If you want to work in NASA, is it better to do your PhD in an Indian college or an American one? Okay. This is an interesting question. So a PhD is a PhD. So a PhD means you have to put a lot of effort in understanding the particular problem which you want to solve. So that no matter whether you do it in Indian college or American college or European college, that is up to you. So when you try to learn more and more during your PhD phase, that means that is the knowledge which you gain, so which is going to be useful. I think that is the best way I would put it, that no matter where you do your PhD, so it's the amount of knowledge which you get and the breadth and the depth of knowledge which you get is what is going to take you. I think with this, it's a very interesting session. I really appreciate all of your patiently listening and then understanding the concepts, taking all the questions. It's really fascinating to look at all your questions in the chat box. And once again, on behalf of the Let's Talk Astronomy team, so I thank you for attending this session, and keep watching our webpage where we keep updating some of the FAQs, which many of you guys have asked. We didn't get much time to answer. So for any questions and suggestions, and we welcome your feedback. So we need you. We need your feedback. So please write to us at this. Our email address is here, askastronomer@gmail.com, and keep visiting our webpage where we will upload some of the interesting questions and answers from field experts. And also we would be putting some of the interesting facts or useful information about astronomy. Yeah. Thank you very much for participating in